We know that arc length equals the integral from a to b of the square root of dx dt quantity squared plus dy dt quantity squared dt. Okay, and this is assuming we have a curve in the 2D plane that's parameterized with functions x of t and y of t. And we're going to have one extra restriction if we think about this. I'm not going to write it, but I'll say it. The curve's not allowed to move backwards on itself. Okay, otherwise, you end up with some problems. Like, in other words, as we traverse this curve through space, here's your axes, pretend, and then your curve does something like this. What we're going to say is pretend this is where t equals 0, and then somewhere over here is some other value of t, maybe t equals t1. But the following will be true. This thing moves, as this object moves along this curve, it will not stop, it will not move backwards. And that would play havoc with our integral, because what the integral does is sort of, it's adding up all these velocities times. So if you let it move backwards, like if it's moving along like this, everything's fine. But if you let it move backwards for a minute, and say it came back, we would add that distance on and then add it twice. So that would be a problem. It would screw up the arc length. So we're going to require that both of these derivatives, dx dt and dy dt, remain greater than 0 for the entire time that we're interested in finding the arc length. So let's state a goal. The goal is going to be to use this integral to find a length of sort of one arc of the cycloid. So here's the cycloid, right? The thing that we get when we let that circle roll along the x-axis, and we pay attention to a point on the circumference of the circle and say, how high is it above the x-axis for any given time? We showed how we could use vectors to get this equation, these equations. Here we go. X of t was equal to that, and y of t was equal to this. Okay? So my claim is that the answer that we get is kind of interesting. So we'll see what you think. All right, so we're just going to apply our integral and make sure everything is fine. So it's going to be the integral, and it's going to be the square root of, and now I need some derivatives with respect to t. So if t is the variable, and we look at just x of t for a moment, the derivative of r times t would just be t. And then the derivative of sine of t is cosine of t. It would be minus, oh, I said t, that's not correct. I should have said r, thank you. And then this would be minus r cosine t. And that gets squared. Plus. And then if we look at y of t for a moment, and t is the variable, r is a constant with respect to that. So the derivative of r is 0. And derivative of cosine, or in this case you can think of it as like negative cosine, is really positive sign. You might luck out in that case. Even if you got the sign wrong, the sign, you'd square it anyway. So it would be okay. All right? Now, we just need to give a little bit of thought. Don't forget what t is in this case. T was that angle that when we did our parameterization with our vectors. So it would take t spanning from 0 to 2 pi to complete one arc of the cycloid. So all I want to do is some algebra and see if we can figure it out. All right, so we should try and simplify this a little bit and sort of hope for the best. Well, if you look at this, this is r minus r cosine t times r minus r cosine t. And if we square that out, what do we get? We get r squared in that guy, and then we get these two. So we get minus 2 r squared cosine t. And then the last term, so this would be plus r squared cosine squared t. And if I take this term and put it next to it, plus r squared sine squared t, I start to see something that looks pretty nice, right? You see at least one thing. This piece equals, and we think about it, we factor out, right, an r squared, then you'd have r squared times cosine squared plus sine squared t, which is just 1. So you end up with r squared. Okay. So this expression turns into following. 2r squared minus 2r squared cosine t. Okay. And it looks like we have a lot of stuff going on here. But remember, r is just a number. It's a constant. So really, the only variable here is t. Let's factor out 2r squared. So you have 2r squared times 1 minus cosine t. Okay. So let's just make that comment. I'm sort of hinting at you. You should consider this identity. Don't lose track of what you've done. You've done a bunch of algebra here, but if you think about it, we're trying to find the integral from 0 to 2 pi of the square root of this thing. So the square root of 2r squared times 1 minus cosine t dt. And the problem we have is that even though this is just a constant, we can factor that out, trying to find the antiderivative of the rad of 1 minus cosine t can't be done without the way it is. You need to rewrite it. I'm just going to take a minute, and you'll see where we end up with it. I'm going to try and get this expression. I would like to have this 1 minus cosine theta, or 1 minus cosine t by itself, because then I can plug that into here. And then there's a way to get it, right? So let's look at that. All right. So if we do this, I would think you could square both sides to start, right? So you'd have sine squared of 1/2 theta equals 1 minus cosine theta over 2. And then you can multiply both sides by 2. So 2 sine squared times 1/2 theta equals 1 minus cosine of theta. So what does that tell us? That tells us that we can rewrite this thing, that this integral can turn into, or just let's worry about this part of it. This thing can go there, right? So what do you end up with? It's square root of 2r squared times 2 sine squared of 1/2, well, t, keep the variable the same, dt integral 0 to 2 pi. So now you're okay here, right? You can start to take things out. Like, for example, these guys together. So you looked at this. That's really 4r squared. So the square root of that is going to be 2r. And then the square root of sine squared is just sine of 1/2 t dt, integral 0 to 2 pi. So I've gotten rid of that square root, and I have something that I know how to take the antiderivative of. And that's what I was really hoping for. Okay, so I just need to think for a minute about this, and then we'll be okay. I need something to have a derivative of sine of 1/2 t. That's what I need to happen, right? So we know it would have to have been negative cosine of something, because the derivative of negative cosine is positive sine, so we're going to have negative cosine. It's going to have a 1/2 t inside. Then you have to ask yourself, is that going to work out? Well, if you took the derivative of this thing the way it was, the derivative of negative cosine of 1/2 t would end up being, this is just sort of like a temporary check, right? So if I took the derivative of this, I would get the sine of 1/2 t times 1/2. And the problem I have is that there was not a 1/2 there, right? So there must have been a 2 also as part of this antiderivative. I would have had to multiply by 2. And this little part here, this thing here, is just the antiderivative of that piece. It's going to get multiplied by this constant also, so I'm going to have a 2r in front as a coefficient. Okay, so we're ready now, because now if we just combine, we'll do a little bit of multiplying there. We get negative 4r cosine of 1/2 t evaluated from 0 to 2 pi. And the rest is just calculations. So negative 4r, we're going to plug 2 pi in first. We're going to have cosine of 1/2 times 2 pi minus negative 4r, cosine of 1/2 times 0. And look and see what happens here. Surprisingly simple answer. Everything's done. Just think about this term for a minute. That's the cosine of pi. That's negative 1. And over here, we think just about this term. That's the cosine of 0. That's just positive 1. Well, negative 4r times negative 1 gives me 4r. And then we have minus and negative, so it becomes plus. And then 4r times 1 is just 4r. So we get an answer of 8r. So what does that mean? It means that the length of one arc of the cycloid is exactly 8 times the radius of the circle that creates the cycloid. Surprisingly simple answer given how complicated the parameterization is.